The subject of this lecture is electric current. Here I will discuss the historical developments in the science of electricity that led to the discovery of electric current and the devices that are used to carry electric current, which can be used to do various important tasks in technology and everyday life. During the early years of the science of electricity, a discovery was made that was an accidental discovery that led to the development of batteries. Batteries are some of the most important components in contemporary electric circuits. Near the end of the 18th century, an Italian anatomist, Luigi Galvani, announced that an excised frog's leg twitched when he touched it. It was well known from first-hand experiences with static electricity that twitches in humans could result from electric charges. But this was just a leg, so Galvani was convinced that he had discovered the secret life force that he believed existed within all animals. Galvani found that the twitch occurred when he touched the frog's leg with a metal object, but not when he touched it with an insulator. Furthermore, the metal had to be different from the metal hook holding the other end of the leg. It took two different metals to produce the twitch. Another Italian scientist, Alessandro Volta, heard of these results and performed many experiments with sensitive electroscopes, searching for evidence that electric charge resides in an animal tissue. He eventually convinced himself that the electricity was not in the frog's leg, but was the result of touching it with the two metals. Volta tried many different materials and discovered that an electric potential difference was produced whenever two different materials were joined. Some combinations of metals produced larger potential differences than others. One of his demonstrations was to place his tongue between pieces of silver and zinc that were held together at one end. The flow of electricity caused his tongue to tingle. And you may have felt the same effect if you have placed a piece of metal foil in your mouth, touching a filling in your mouth. And so you would get this tingling sensation. Another example of such effect is touching the terminals of a 9-volt battery with your tongue. Of course, the battery already exists, so that's not necessarily a real proof of the galvanic effect. However, the battery is a modern version of the experiment that Volta conducted. So the common denominator in all these examples and experiments was that some sort of chemical process was responsible for the charges moving from one metal to the other, creating a potential difference. Initially, Volta made a single-cell battery by putting a piece of paper that has been soaked in salt solution between pieces of silver and zinc. And then he stacked those cells in a pile, like shown here. And by doing that, he was able to produce a larger potential difference. And this potential difference was equal to the sum of the potential differences of the individual cells. So let's look at one cell. So we have some silver and zinc. So here is the zinc plate, here is the silver plate, and then in between is sandwiched a piece of paper that had been soaked in some salt solution. So the piece of paper with the salt solution provides the positive and negative ions that can flow between the two plates due to the difference in potential because they are made from two different metals. And so stacking these individual cells like that would increase the potential difference between the two ends of this stack as the sum of the individual potential differences for each cell. The potential difference between the two different types of metal is created due to the difference in protons and electrons in each of the two kinds. Another important piece of information that was obtained through experiment was that the voltage produced by a battery cell does not depend on the size of the battery. It only depends on the materials used. A bigger cell will just produce more charge transferred over time, which only increases the longevity of the battery. But it's not going to increase the voltage or the potential difference between the two terminals of the battery. To produce batteries with either longer life or with higher voltage output, cells are connected in two different ways, either in parallel or in series. We will discuss this in the next section. Here is a schematic of a typical flashlight dry cell. The conducting materials here are the carbon core of the battery, and carbon is a conductive material. The other material here that conducts is zinc, and in between the two we have electrolyte paste. The cell is then covered with an insulating material, and so these 1.5 volt cells are often used end to end, usually both pointing in the same direction, to provide 3 volts used in many flashlights. Sometimes these batteries are also used in remote controls or various controllers that require an independent source of power for controlling circuits or different types of devices as well. The voltage produced by a battery cell does not depend on the size of the battery, it only depends on the materials used. So a bigger cell will just produce more charge transferred over time, which only increases the longevity of the battery. It does not increase the potential difference between the terminals of the battery. To produce batteries with either longer life or with higher voltage output, if we only have smaller batteries at hand, cells are connected either in parallel or in series. Let's first talk about the parallel connection of batteries and what that does for the new battery that's created. First, let's define how I'm going to depict a battery schematically. So here is my battery. At the positive terminal we have a metal cap. The negative terminal is the bottom of the battery, which is flat. And then the potential difference between the two terminals is indicated on the battery itself. In this case, for my example, I will use 1.5 volt batteries. Connecting batteries in parallel increases the life of the new battery. The voltage, however, remains the same. And parallel connection is achieved by connecting the positive terminals of the battery and the negative terminals of the battery. So let's see what that looks like. So let's connect 3 1.5 volt batteries in parallel. According to the definition, the positive terminals of the batteries are all connected together. So if I get a wire, I will connect that wire to the positive terminals of the battery. And then the negative terminals of the batteries are also connected together. So I will take another wire and I'm going to connect the negative terminals of the batteries. This will result in a battery with the same potential difference, but with larger output of charge, which means that you can imagine that these 3 batteries just became one big battery which contains more charge, but it still has 1.5 volts potential difference between the terminals. And so to summarize, connecting batteries in parallel increases the lifetime of the battery while the potential difference remains the same. The other type of connection that can be achieved with batteries is the series connection of batteries. The series connection is achieved by connecting the negative terminal of one of the batteries to the positive terminal of another. The result is a battery with higher potential difference, but with the same lifetime as an individual battery in the connection. Here is my 3 1.5 volt batteries. I want to connect them in series. From the definition, I must connect the negative terminal of one battery to the positive terminal of another. So I will take a wire from the negative terminal of the first battery and connect it to the positive terminal of the second battery. Then I will take another wire and connect the negative terminal of the second battery to the positive terminal of the third battery. As a result, I'm going to get a battery that will have .5 volts of potential difference between the positive and the negative terminal, but the lifespan of this battery is going to be the same as the individual batteries in the connection. Another way to schematically represent this connection would be something like this. The batteries are just simply connected by making contact between the negative terminal of one and the positive terminal of another. This type of arrangement is observed in flashlights, for example. Electric charges, when subject to a potential difference, will move between 2 points of space. As a result, the charges gain energy, which can be used to do work or convert to a different kind of energy. For this process to take place, the electric charges need a means to travel between 2 points in space. And conducting wires are the means of transportation of electric charge. The energy carried by the charges is utilized by what we call a load, or multiple loads connected to those wires. And the energy carried by the charges is converted to either mechanical work or heat or light by these loads. A device which can transport charges to between 2 points in space so that the energy carried by the charges can be used is called an electric circuit. Let's look at the basic components of a simple electric circuit. First, we need a source of charges. And this source can be either a battery of some sort, the power grid, or an electric generator, for example. Depending on the source, different amount of charges will be provided in the circuit. And so the type of source is also determined by the purpose of the circuit. Big circuits that require lots of charge will have sources that provide more charge compared to small circuits that do not require a lot of charge. For example, the circuit of a flashlight requires only a couple of batteries to operate for a while. The electric circuit in a house requires a lot more charges, and therefore that cannot be provided by some batteries. It requires connection to the power grid of the city where the house is. The second component necessary for a circuit to be operational is the conductors for charges, or in other words, the wires. Wires are made from metal, and the typical metals that are used for contemporary circuits are copper, silver, or gold. The most common material is copper because it is cheap to use and provides a very good conductivity for the electric charges. Of course, gold is probably the best material in existence. However, it is very expensive, and so it is used only in specialized circuits, such as cell phone circuits, computer circuits, for soldering chips to the motherboard, and so on and so forth. And then the last component of a simple circuit is the load or loads. A load is a device that is going to utilize the energy carried by the electric charges and either convert it into mechanical work or heat or light. Several examples of loads for circuits are the electric motor, a light bulb, different types of appliances. A very important principle necessary for the operation of electric circuits is the principle of conservation of charge. The principle of conservation of charge simply states that in an electric circuit, charge is never lost or used up. The number of electrons leaving the one terminal of the battery is equal to the number of electrons entering the other terminal of the battery. And what is used up is the energy that these electrons carry, and this energy comes from the power source. So that could be the battery of the circuit, or it could be the power grid if the circuit is connected to the power grid, and so on and so forth. So the number of charges that circulates in the circuit is constant at all times. Charge is not lost. Let's discuss how a simple circuit is constructed with a battery, a set of wires, and a light bulb. First, let's explain what a light bulb is. A light bulb is a simple device that consists of a wire that enters the light bulb, and then another wire that exits the light bulb to the side. The two wires are connected by a very thin filament, which, when electric charges flow through the pathway provided by the wires and the filament, causes the filament to glow due to the amount of heat that's generated by the charge flow here. How bright the bulb is depends on the size of the filament and also the amount of charge that passes through the filament. So, a light bulb is a typical example of a load for an electric circuit. Now let's see how we can complete an electric circuit so that the light bulb lights up. Here is one example of a connection for the light bulb and the battery. So one of the terminals of the battery is connected with the wire to the side of the light bulb. And we know from experience that this type of connection is not going to produce any light in the light bulb because the pathway of the charges here is interrupted since the wire that's coming out of the bottom of the bulb is not connected to the battery. So if I assemble my circuit like so, this is an incomplete circuit, the light bulb is not going to light. On another hand, if I connect the bottom of the bulb to one of the terminals of the battery and then the side of the bulb to the other terminal, that will result in the light bulb turning on. The same effect can be achieved by making contact between the side of the bulb and one of the terminals and connecting the bottom of the bulb to the other terminal. This is a complete circuit where the electric charges will flow inside the wires, will pass through the light bulb, through the filament, and back into the battery. So the charges are going to deposit their energy in the filament, which warms up, heats up, and then as a result, it glows. An example of a practical circuit that actually can be turned on and off is shown in this schematic here. So we have the battery. The positive terminal is connected to the bulb with a wire. So that ending here connects to the side of the bulb. The other ending connects to the bottom of the bulb. Then we have a gap, and then in the wire, and then the wire continues to the negative terminal of the battery. So in this particular situation, where this gap is not filled by another conductor, this circuit is not going to work. The light bulb will remain dark. However, if I manage to place a piece of conducting material to connect the 2 points in the gap, that is going to complete the circuit. Electric charges will flow in the circuit. The light bulb will turn on. And so a simple device that can be used to selectively open or close this gap is an electric switch. And so even though in our households this is much more complicated circuit, the basics of turning on the lights is essentially this. You flip the switch, you close the gap, and then your energy source, which is the power grid, powers the circuit, and then the light bulbs in your living room, let's say, turn on. And then you flip the switch to open the circuit, the flow of charges stops, the light bulbs turn off. So when we have a complete circuit, charges flow in the wires of the circuit, and the flow of charge in the wires is called electric current. Let's look at the mechanism of charge flow in the wires. Let's look at the mechanism of charge flow in a circuit. Remember from before, we talked that in metals, the atoms that make the crystal lattice of a metal are fixed in space, and the nuclei of those atoms are also fixed in place, and they cannot move. So in the nucleus of an atom, we have positively charged particles. The protons, those are fixed in place, they cannot move. So therefore, these are not the carriers of electric charge in metals. However, the electrons that orbit around the nucleus of an atom can hop from that atom and move around in space in the crystal lattice until they hop on another atom. And so this motion of these electrons is these free electrons is how the charge is carried in a wire or a metal in general. So let's try and visualize what these free electrons look like in a piece of wire. So here's my piece of wire, and these are the atoms of the crystal lattice of the metal from which this wire was made. And so we have a bunch of free electrons that are wandering around in the crystal lattice. And the direction of motion for the electrons is random. So they do not move in one preferred direction. They just move very randomly. And the change in direction as they move happens only through collisions with other electrons. Or if one electron hops on an atom and another is released, it's going to move in a certain in a random direction. And so let's see now what happens if I connect a power source, or in other words, a battery, to the two ends of the wire. So here is my piece of wire, and I've connected it to a battery like so. Now I have provided a potential difference between this end of the battery and that end of the battery. And this potential difference will be equal to the potential difference of the battery itself. And just for the sake of the example, let's say this is 1.5 volts. Alright, so this is going to cause these electrons, these free electrons here, to move inside the wire. What's the direction in which those electrons will move? Well, simply, since these are negative charges, they will be repelled by the negative terminal of the battery. So the electrons will move to the right in this particular example. Essentially, they are moving towards the positive terminal of the battery. So the electrons are going in the circuit like so. Now, this organized motion of electrons in that particular direction is what the electric current in the circuit is. The electric circuit in a wire is defined as the amount of charge per second that passes through the cross-section of that wire. So then imagine that this is a piece of wire, and I can measure the amount of charge that passes through the cross section of the wire. So this cross section here. So let's say that the amount of charge that passes is capital Q. And then I also measure how much charge passes through that cross section in 1 second. So then I can define the electric current, I, as the ratio of the amount of charge per unit time, so for 1 second, and the units for that will be coulombs per second. The units of charge divided by the units of time, seconds. A common unit that is used for electric current is not coulombs per second, but the ampere. And this unit is named after a French physicist who discovered the properties of electric current. Another property of electric circuit is the resistance to flow of charge. Just like many other physical phenomena, the process that is happening is not free of resistance to the process. In the context of electric circuits and the flow of charge, the wires themselves resist the flow of charge. The flow of charge is not unimpeded. One reason for the resistance in a circuit is the fact that the free electrons that carry the electric current or that make the electric current undergo collisions with other free electrons as they all flow in the wire. So when these collisions happen, the direction of motion of the electrons changes a little bit, and until they correct their direction of motion due to the potential difference between the ends of the wire, essentially the flow of current is decreased since some of the electrons are not moving in the common direction of all electrons. Another reason for the resistance to flow of charge would be that free electrons will hop on atoms that have vacant spots. So remember that the free electrons are the result of electrons that are further away from the nucleus of an atom hopping off of that atom, and so they move free in the crystal lattice of the wire. But if they encounter another atom with a free spot for an electron to land, under the right conditions, that electron will hop on that atom. And so there is a constant sort of exchange of free electrons between atoms. And so when electrons hop on an atom, or multiple atoms of course, that is essentially a decrease of the amount of free charge that's flowing in the wire. That is then part of the resistance to the flow of electrons in that wire. So these two main reasons here are related to the nature of the electric current and electric charge. But there are also mechanical properties associated with the wire itself that affect the resistance to flow of charge. The factors that affect the flow of charge in wires are the length of the wire. So the longer the wire, the higher the resistance for the flow of charge. The shorter the wire, the smaller the resistance. And so the reason for that is that when the wire is longer, there are a lot more atoms there available for the free electrons to hop on, or in other words, for the amount of charge flowing through the wire to decrease. The diameter of the wire is also a factor in the resistance to the flow of charge. The larger the diameter, the smaller the resistance. Think about it this way. Imagine that you want to pass 1 gallon of water through a pipe that has a diameter of 1 inch. So it's going to take a certain amount of time for all that water to pass through that pipe. Now imagine that you increase the diameter of the pipe to 10 inches. In this case, it's going to take much less time for the water to pass through the pipe. So the analogy here is that if the diameter of the wire is bigger, then there is a lot more space for the same amount of charge to pass through that compared to a wire with smaller diameter. When the diameter is larger, that amount of charge has much less chance to be decreased by electrons hopping on atoms as the charge passes through the wire. And then the last factor is the material from which the wire was made. So, for example, gold is much better conductor than copper. So depending on the material from which a wire is made, that will also determine what's the resistance to the flow of electric current. The symbol that is used for the resistance of a wire is capital R, and the units are ohms, or can be also written like so. So the unit is named after a physicist who was able to determine the relationship between the current, the resistance of a wire, and the potential difference between the two ends of a wire. Or in general, the potential difference in a circuit, the resistance of the circuit, and the current in the circuit. This relationship is known as Ohm's law. So Ohm's law states that the potential difference in a circuit is equal to the product of the current in the circuit and the resistance of the circuit. We're going to use this definition to analyze simple electric circuits. I will demonstrate this analysis in the second part of the video, where I'm going to discuss the two main types of circuits that exist. Those are the parallel and the series circuits.